Okay, so we have our anti-carbon product. Um, so let's look at the mechanism. Again, this is opposed to any reaction that does, if we want anti-carbon to cause addition of water, we use hydroboration oxidation. Okay, so let's look at the mechanism. Alright, so let's say we have this alkene here. Scratch that. Let's say we have this alkene here. Yeah, that's okay. We can do that. Okay, so we're gonna take BH3, and in a concerted process, we're gonna since this has, remember, that empty p orbital, it can accept a pair of electrons. So this electron density is gonna come here, and now hydrogen is actually gonna act as a nucleophile and attack here in a concerted process. Okay, so that leaves us with this is, I don't know what that is. I don't know. It's 2BH2 to give us an alkyl borane. Okay. All right, that's what we have, an alkyl borane. Okay. Notice that the boron added to the carbon with the greatest number of hydrogens. Okay, again, that's because it's acting as an electrophile. The electrophile always adds to the carbon with the greatest number of hydrogens. So taking our alkyl borane that we have, this right here is going to serve as what we call, is going to equal to R. Okay, so we're going to say BH2R, an alkyl group. Okay, so we're going to repeat this process again with the double bond with our same alkene that we had. And we got BHR. Okay, same process. Attach this, this attacks that, and we are here now. Matter of fact, I forgot to put that there. Okay, forgot to put that there. Okay, I also forgot to put it on this, on the other one too. Okay, but we know that that attack, it adds there. Okay, so that leaves us with, in the concerted process after that, we have CH3, CH3, C, B, R, H, 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 and again we're here again. Okay, so again this serves as our R group, same thing as we had last time. So now we have a dialkyl borane, which would be abbreviated as BR2H. So we'll repeat that one more time. So we'll go back to an alkene, BR2H, text there, leaves us with C, CH3, H, C, H, B, R2, right? Okay, so now again we have our third R group that includes that H2, which now we have BR3. Okay, well each R group being the same as these. Okay, not gonna draw it all the way out. Okay, so now we have that. We understand why we did that and why it follows anti-Markovnikov rule. One, that when we follow this the way it lowers the transition state, and also these bulky groups account for sterics. For example, we explain the first, meaning through the transition state, anti-Markovnikov. So why anti? Because if we look at the transition state here, we have the CH3 is going to be the same explanation as we always been saying. H, transition state always showing the bonds breaking and the bonds forming. No full charges develop in a transition state, only partial charges. So if we form that bond here with the BH2, okay, along with that hydrogen that's going to form that bond here, this bond, the way I have it drawn, is formed a little bit more than this bond. As you can see, this is at an angle, so this is a little farther apart than this bond. So just like when we add hydrogen to one of these carbon and it always form a carbocation on the other charge, if this bond is almost formed before this bond, then that puts a partial positive charge here. Okay, if that puts a partial positive charge here, that means that these methyl groups, okay, are going to stabilize that partial positive charge. Okay, versus if it was the other way around, this if this bond formed first and this one was down below, not fully formed, then the partial positive charge would be over here, but this transition state will be higher in energy because of these two hydrogens cannot donate to support that positive charge. Okay. Also, whenever boron has 4 bonds to it, it develops a negative charge. So since we have 1, 2 with H2, 4, 1, 2 makes 3 and 4, then this has a partial negative charge on there as well. Okay. So this is why it goes through anti-Markovnikov rule, because the addition to this way allows this to have a lower transition state. Now the reason why we go and change BH2 to BR3 is because now with this BR3, we know the size of our R groups. They're very, very large like this. Okay, so we have these large R groups over here. This prevents, with this CH3 group, these CH3 groups are larger than these hydrogens. Okay, so this boron, once it comes with BR3, not only does addition to this carbon with the less hydrogen is supported by it provides support to the partial positive charge. Not only that, but we have what's known as a steric effect. This BR3 can easily attack this because of these small hydrogens, but it would be difficult for it to attack on this side with those methyl groups and these alkyl groups. Okay, it's not enough room over here. So steric is a space filling opportunity. So this is more space for this BR3 to fit here in comparison to here. So there's two arguments. First argument, lower antimicrobial cough, it lowers transition state. 2, the steric effects support addition of boron to carbon with most hydrogens. Okay. So you should be able to explain that. Why does it go through antimicrobial cough rule? 1, because the sterics associated with this, and 2, the transition state is lower because this bond is formed, so it forms a partial positive charge. This bond is formed a little bit more than this bond, so it forms a more partial positive charge on this carbon, which is supported by back donation or hyperconjugation to this carbon, okay, to this partial positive charge. So now that we have our Br3 group, let's continue with the mechanism. Which would be the second part. So we have the Br3 okay, plus hydroxide ion, usually be a sodium hydroxide, okay, plus peroxide H2O2 in water, okay. So that's going to yield an alcohol plus BOH4 and boron. Whenever it has 4 bonds, it has a minus sign on there, okay. So this is the oxidation step. We done the hydroboration. Then we added a hydrogen and a boron to it. Now we're going to do the oxidation, okay? So if we have this peroxide, let's say we have this, which is peroxide H2O2. We have this hydroxide ion here, okay? Sodium hydroxide. Okay, plug that off here, gives us right. I'm trying to get it all in the picture. Okay, that's what we have. This anion has to be paired with a cation. Okay, so but the sodium is not just, it's like a counter ion. I mean, it's like a spectator ion. It's not really participating. So this here plugs that hydrogen off and produces that peroxy anion. All right, so with our peroxy anion, we're able to take our Br3 plus and we remember this has that empty orbital on to accept that pair of electrons, so we're going to attack that. We here. All right. Come on. All right. So now we're going to do, we have this here. We know that this bond is very, very weak. And then also this has a negative charge on it because it has 4. So which is not too bad. It's okay with having 4. But we do a 1, 2 alkyl shift. Here. Plug that off, okay? Now oxygen is okay with having a negative charge on it, just does not like to have a positive charge on there. So here we are here, here, and we'll get OR, okay, plus a hydroxide. Okay, so we get the hydroxide, they can go back and produce another peroxy anion. Okay, so we get this, will plug that off there, okay, which gives us, now we have B, R, OR, and R plus OOH. Again, this is going to attack here, giving us now we have our negative charge on here again, so we're going to do a 1, 2, another 1, 2 alkyl shift. Well, this goes here, plugs that off, give us okay. So I'm not going to show the production of the peroxy anion again. I'm just going to put it here, which is fine with me. Once you show it once, you don't have to show it again. So we do it a third time. Okay, that's the peroxide addition, OOH right there, ran a little bit out of room. OR. I'm going to do another 1, 2 alkyl shift where this methyl group contact this oxygen and push these electrons there. Okay. So now we have B, OR, OR, OR. You also see it written as BOR3. Okay. Now, here we have BOR3. Get another sheet of paper. Okay. Now we have BOR3. Those hydroxide ions that we had are available still. Okay, got BOR3 hydroxide. Remember, we still have these in solution, right? So these will attack here. And once those attack, then this pops off. That gives us B, O, H, B, O, R, B, O, R. Okay. That would B, O, R, anion. Remember, R is a big alkyl group. Oh, I'm sorry you guys can't see that. So I'll do it again. Actually, no, I'll just explain what I did. Okay. So this is OR here. OR, okay? So we have BOR, BOR, the hydroxide attack there, and this is popped off, so we have this. Now what happens is, this OR group, which is R group, was equal to that big methyl group that we had in the beginning. So refer to earlier notes. Oh my goodness, what's going on here? Okay. So now this R with this minus sign on these on this oxygen is going to pick one of these off and put this back here. Okay, so now we have B OR O minus and then OR. Okay, so the same thing is going to happen. We have another OH hydroxide anion. Again, it's going to attack here. I'm going to push one of these off. And we're going to get B O R O H O R. Okay, and since we popped one off, sorry, this is actually just O. Since we popped one off, this is what we have here. Same thing happened. It takes this hydrogen and pushes the electrons back in. Electrons to this bond back here. Same thing occurring. So now we're left with B O minus O minus and OR plus basically 2 ROH. Okay, because we produced a ROH here, we produced that there, even though I didn't show it here, and we produced it here when we plucked that one off. Okay, so let's look at the next one. Do the same thing again. We got the hydroxide anion. Okay, so we'll attack here, pluck that off. It gives with B O minus O minus O minus and left with not O minus, OH. And the OR that was plucked off here comes back in again, attacks that hydrogen, and this bond here goes back there. So now we're left with 3 alcohols, 3 moles of alcohol plus B O minus. Okay, now remember we have water in solution. We have peroxide in solution, not water. We also have protonated water. That these are protonated water and hydronium ions that these anions can come and attack. Now, what I would like to see if you guys get this far to produce these 3 alcohols and this, that would be very, very good. If we got any question, if you can complete the reaction, it'll be even better. But you need to see that you're gonna produce this. Okay, that'll be very, very essential to see you producing these 3 moles of alcohol and going through this process. Okay, so we go back and explain this. Once we get our B OR3, okay, we simply use the hydroxide anions that we produce in attack to pluck these ORs off. The OR comes back and removes a proton. Simple as that, 3 more times to produce the alcohol, ROH. Okay, that's all we did. Here, same thing. Once we got one of the ORs off, we come back with a hydroxide anion that we produced. In the first reaction, we plucked out the peroxy anion, and we attack here, pluck that off, and we produce our other alcohol. We produce our OR group to get that, and we produce another alcohol. Okay, just take practice. You have to go through and write. All right. So what else we got next? The last one, hydrogenation. Very simple. Hydrogenation of alkenes. Okay, so really addition of hydrogen. Okay, here's the template, which is CH3 plus H2. Scratch that. Scratch this. Okay. Plus H2 yields. Now this reaction can only occur with the use of a catalyst. You have a platinum on carbon catalyst, and you can also have a palladium on carbon catalyst. Okay, what that does is allows the reaction to occur where you have this addition of hydrogen across the double bond. Okay, the reaction mechanism is not really known for this reaction, but through these catalysts, we know that they lower the transition state or lower the activation barrier for this to occur. This cannot happen without a catalyst. A hydrogen-hydrogen bond is very, very strong, so we're not going to simply do the mechanism like we usually see, where we break the bonds apart and then add one at a time through a stepwise process. The bonds are entirely too strong. So these catalysts, the platinum on carbon and palladium on carbon, are known as heterogeneous catalysts. They are insoluble catalysts. Therefore, they are easily separated from reactions. Kind of like oil and water, easy to separate. Okay. What they believe happens is, in a mechanism, you may have, let's say, this would be your carbon source, okay, and your palladium catalyst, palladium on carbon here, okay, like a surface, and you have hydrogens that are absorbed on top of this surface. Okay, yeah. What happens is that the alkene will align itself on top of this catalytic surface, and the hydrogens will begin to attack. The hydrogens will begin to add to the double bond to give you your product. Now that's an illustration of the catalyst, whether this is palladium carbon or platinum carbon. So to give just some sort of a mechanistic view, it would look like this. Very simple, straightforward. We would say that, and And that might be a little confusing, so I'm just gonna draw the hydrogens out, okay, like that. Okay, so let's say this bond just breaks here and one electron goes there. So this dot counts as one of the electrons, and let's say one of them goes here. Okay, and then let's say our hydrogen, which we know only has one electron, it aligns itself with these carbons. Okay, same thing I said in the picture. It aligns itself with those carbons, and therefore it gives us our product, which would be C so that's catalytic hydrogenation of a double bond. We'll look at one more thing concerning catalytic hydrogenation. This reaction, once it's done, it releases heat. Okay, this heat is called heat of hydrogenation, which is the same thing as the enthalpy value. Okay, use this, and so it's the same value as the enthalpy value, but the heat of hydrogenation is positive. While since this is, but the hydrogenation acts an exothermic reaction, which we know exothermic reactions are negative. So depending on what terms you're talking about, if I ask you what's the enthalpy value, you know it'll be a negative value. What's the heat of hydrogenation, you know it's a positive value. Okay, what I want to show you is that we don't know the mechanism, so we cannot really draw a reaction coordinate diagram, but we can look at the stability of the alkene versus the alkane. We can look at the stability versus the reactants and the products, okay, to determine which reaction will be more favorable. Plus, so let's just look at it and then I'll explain further. So if we were to look at a potential energy diagram here, we'll put potential energy. Okay, and let's say we had let's say we're gonna have three different alkenes. Okay, we have this first alkene where it is okay, zoom in so you can see. All right, so let's just say this enthalpy value delta H is equal to negative 30.3 kcal per mole. Okay, now this is delta H, so the heat of hydrogenation will be positive 30.3 kcal per mole. Okay, that'll be heat of hydrogenation. Now let's look at comparative. We had just we will discuss in class. We'll discuss this in class, okay? Because we haven't went over. But that will be the material for your test. The first video along with this video. I hope you guys will study. And good luck.